Welcome all to the second part of section 16.8, relative motion analysis using rotating axis. So as I discussed in the first part, this session is going to be dedicated for one complete problem. So let's start this example. So at the instant shown, the rod AB right here has an angular velocity omega AB, which is equal to 4 radian per second, and an angular acceleration of 2 radian per second squared. We would like to determine the angular velocity and the angular acceleration of rod CD at this instant. The collar C is pin connected to CD, so this one is pinned over here and slide freely along AB. Now, by analyzing the motion of point C, we can observe that it is sliding along AB at the same time it is rotating with it. And for that, we would have to use the relative motion equations with rotating axis. So what I am going to do now, I'm going to write the velocity and the acceleration equations between point C and point A, because point A is fixed. That's a good point. And the other part is that we know alpha and omega for AB. If we do it between C and D, we will have too many unknowns. So let me write down the equations. VC is equal to VA plus capital omega cross RC with respect to A plus VC with respect to A as measured from the local coordinate system, small x, y, and z. Now, the acceleration AC is equal to AA plus capital omega dot cross RC with respect to A plus capital omega cross capital omega cross RC with respect to A, and then 2 capital omega cross VC with respect to A as measured with respect to the local coordinate system, small x, y, and z. And finally, the acceleration term AC with respect to A as measured with respect to the local coordinate system, small x, y, and z. So now, let's start analyzing those terms. But before we do that, let me explain why I established the coordinate system as shown here in red. First, point C is at this instant is sliding along AB, so we understand that the local coordinate system, small x, small y, would be attached to AB and it will rotate with it. Now, what we did here differently is that I attached the fixed frame of reference to AB at this instant, so it will not rotate with it. It is fixed, but it is initially oriented this way. So this is to simplify the calculation. Now, if we analyze the terms on those equations, we have VA, which is equals to 0, AA, also 0, and then we will have capital omega, which is equal to 4k radian per second, and we will have capital omega dot, sorry, I forgot to put the arrow for the vector, which is equal to 2k radian per second square. Also, we can see that R C with respect to A, which is the vector going from A to C. So the vector going from A to C is equal to 0.75 I, and this is measured in meter. Also, we can understand that VC with respect to A as measured from the local coordinate system has some magnitude VC with respect to A x, y, z, but its direction is y. Also, the acceleration a c with respect to A as measured from the local coordinate system equals to a c with respect to capital A, small x, y, and z, and this one also have a direction I. Why? Because with respect to the local coordinate system, C is just translating along the I component. And also RC with respect to A, which is this vector, is simply measured as 0.75, which is the length, and this component is I. Now, if we consider link CD, then this link has a motion which is only rotation about a fixed axis. And for that, the equation can be written as follows. VC is simply equals to omega CD cross RC with respect to D. And the acceleration of C is equal to alpha CD cross RCD minus omega CD square multiplied by RC with respect to D. So if you look carefully here, we have the simple velocity equation because C with respect to D is just rotating about a fixed point. And the acceleration, when we have fixed point of rotation, then the acceleration will have a tangential component, alpha r, and this is tangent, and then a normal component, which is omega square r. Now, we need to identify this position vector. This position vector, as we explained before, is going from D all the way to C. So this is the position vector. This is R, C with respect to D. So if I want to write the component as this is the arrow, then I would have to have this is the J component, and this is the X component. So this is the X component, and this is the Y component. Clearly, both of them are negative. Since this angle is 60, then this angle is 30. So if I want to write down the position vector R C with respect to D, then it is equal to minus 0.5. 0.5 is the length of this part, which is 0.5 meter, and then it's cosine 30 I minus 0.5 sine 30 J. This is in meter, so what would I get? I will get minus 0.4 33I minus 0.25 J meter. Now, if I substitute this in the above equations, I will get VC, which is equal to minus omega CD by K cross minus 0.433I minus 0.25 J. Now, if I solve this, I will get minus 0.25 omega CD in the I direction plus 0.433 omega CD in the J direction. Of course, I got omega right here as negative because it is rotating on a clockwise fashion, which is negative with respect to our convention. So I'm going to do the same. I'm going to write down the acceleration equation by substituting the position vector. So what I'm going to get is AC, which is equal to minus alpha CD, and this is the position, the vector direction K, cross minus 0.433I minus 0.25 J, and then I have the minus sign, omega CD square multiplied by minus 0.433I minus 0.25 J. So I will get the acceleration as 0.433 omega CD square minus 0.25 alpha CD. All of this is the I component, and for the J component I will get 0.433 alpha CD plus 0.25 omega square CD. This is the J component. Now, if I substitute the previous equation of VC with the first one, I will get the following. So in the first equation, we said VC is equal to VA plus capital omega cross RCD plus VC with respect to A. Sorry about this. C with respect to A as measured from the local coordinate system. So from the relation of VC with respect to D, we can relate this with the equation when we wrote the velocity of C with respect to A. And from that, I will have minus 0.25 omega CD, and this is I, plus 0.433 omega CD J, which is equal to. So now all of this is VC, which we obtained when we wrote the relative velocity between C and D, because you see this is double omega CD and this is omega CD. Now let's substitute the rest of the equation. VA is 0, so we will get 0 plus 4K cross 0.75 I plus V as a scalar, C with respect to A as measured from small x, y, and z, and we also determined that its direction is I. So I would simplify this and get minus 0.25 omega CD I plus 0.433 omega CDJ, which is equal to V C with respect to A as a scalar, and this is its direction, unit vector, plus 3J. So if I equate the I component with the I component, the J component with the J component, I will get the following. I will get from the I component VC with respect to A as measured from the local coordinate system is equal to minus 1.732 meter per second. And I will get omega CD, which is equal to 6.93 radian per second. Now, similar to what I did with the velocity, I wrote the acceleration of point C using point D and point A. So first we started with the acceleration of C with respect to A, and then we wrote the acceleration of C with respect to D. Now we need to add these two equations together, and what we will have AC, which is equal to AA plus omega dot cross R C with respect to A plus omega cross omega cross R C with respect to A, and then we have 2 omega cross V C with respect to A as measured from the local coordinate system plus A C with respect to A again as measured from the local coordinate system. Now what are we going to do? We will write down the left hand side as a function of CD, and we will keep the right hand side the same. So from the calculation that we got before, we had 0.433 multiplied by 6.93 squared. This is what we just calculated, which is omega CD, and then minus 0.25 alpha CD, and all of this is the I component, plus the J component, which is 0.433 alpha CD plus 0.25 multiplied again by 6.93 squared, and this is the J component. So again, 6.93 is omega CD. All of this is equal to 0. Now we are starting with this part. So the acceleration of A is 0 plus 2k cross 0.75 I plus 4k cross 4k cross 0.75 I plus 2 multiplied by 4k and crossed with minus 1.73 I plus AC with respect to A as a scalar measured from the local coordinate system with direction I. Now we need to clean this up, so we add all component or similar component together and we will have 20.78 minus 0.25 alpha CD, and this one is an I component, plus 0.433 alpha CD plus 12, and sorry about this, and this is the J component. All of this is the left hand side, which is equal to AC with respect to A as measured from the local coordinate system minus 12 I minus 12.36 J. So again, we have to equate the I component with the I component and the J component with the J component, and by doing so we will have AC with respect to A as measured from local coordinate system equals to 46.85 meter per second square, and we will get alpha CD, which is equal to minus 56.2 radian per second square. This is the end of the problem. Thank you.